Hi, my name is Madison Matthews, and this is my Physics 2211 Lab 3 report on black hole and orbits. So first, a brief introduction. The purpose of this lab is to demonstrate and understand the forces acting on objects, and we did this through two different parts. So the first part, we analyzed the motion of a star and then estimated the mass of a black hole. And then the second part of this lab, we used given masses of a planet, a moon, and a spaceship to determine the initial velocity of the spaceship that'll get it to orbit both the planet and the moon without crashing. And then we calculated the forces on the moon and the spaceship and used Newton's second law and the position update formula to make the moon and spaceship move. And we did all of this using GlowScript. And then for part one, the system is the star and the surroundings are the black hole in space. So the fundamental physics concepts used here are Newton's second law, where F net equals the parallel and perpendicular components of the force. Then we also use the gravitational force equation, the parallel net force and perpendicular net force equations, the velocity update formula where you take an initial velocity and then use delta time and the F net to get the final velocity, and then the position update formula where you use initial position and then average velocity and change in time to get final position. So here's my GlowScript model for part one, and as you can see, we use the gravitational constant and then the mass of the star, we input it up there, and then filled out all of this code to create equations for initial and final velocity and then initial and final momentum vectors. And then we calculated dp dt and used Newton's second law to calculate F net. And then we also calculated F net parallel and F net perpendicular, and then created a little model in GlowScript that you can see right here. So we calculated F net final, the parallel and perpendicular components of F net, and then from that we were also able to get the approximate black hole mass, which you can see on the left side over here, and then on the right side is just a model of this scenario. So then we created a GlowScript model for part two, where we had the initial conditions, as you can see on the top of the left picture. So we had all the masses of the planet, moon, and ship, delta t, and then the gravitational constant. And then we created, or actually there were initial conditions for the moon and then the spaceship. And then over here on the right side is where we edited the code. So we found a bunch of different forces. We found the net forces on the moon by finding force of gravity on the moon by planet and by the spaceship, and then finally F net on the moon. And then we did the same or similar procedure for the spaceship. And then we also applied Newton's second law in the position update formula to help us calculate everything. And then over here, you can see the moon's orbital speed, the moon's orbital period, and then the moon, spaceship, and planet from the GlowScript image. So possible sources of error that we ran into during this lab are that for part two, we used guess and check method to find the spaceship velocity and determine what velocity would allow the spaceship the spaceship's orbit to be affected by the moon and the planet. And then also we only assumed that the only forces were the ones considered in the code, and because this was a computational model, it's only going to go off of what we input in the code, so there could be other forces acting on things that we didn't consider. So two what-if questions. The first one is, how are net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? And the answer to that is that they're the same mathematically, but for the rate of change of momentum, you only need the change in velocity in the overall system to calculate it, as opposed to net force where you need all the external factors acting on the system. So the rate of change of momentum is easier to calculate than the net force and all the components of that. And then the second part is, if you wanted to predict the motion of the entire system, what would you need to include in your computational model, and would there be any dominant interactions, or would they all contribute more or less equally? And the answer is you would need to include all parts of the surroundings that are acting on the system and all parts of the system acting on the surroundings, and the dominant forces would be between the star, moon, planet, and the black hole. Thank you.